During this session, what I really hope to do is extend our thinking about climate models and make or develop a slightly more effective one that we've used before. Okay? So first of all, let's think about what a climate model really is. We know that models are simplified representations of the real system. Okay? It's always going to be heavily simplified, particularly for us to be able to show it mathematically within an IB exam. Nevertheless, if we do have a suitable model, it allows us to make some predictions about climate on planet Earth. And for this to be in place, we need a set of equations which represent how the atmospheres and the oceans behave, and how temperatures and patterns develop, how winds blow, how everything is involved. Now, as I said, we need a simplified representation. So we're going to look for some fairly simple equations and thinking about how this works. So what you've seen so far is the energy balance model. We recognize that if we know the radiation from the heat and we know the radiation going out from planet Earth, we can work out the temperature of planet Earth. This means that temperature of planet Earth is a steady state, and we have done some calculations on that, and we recognize that the temperature involved in that is just not big enough. Okay, and one of the main reasons for that is because we're not looking at or not incorporating a feature of planet Earth warming up because of heat energy getting captured in its atmosphere, and the planet warming up as a whole. So for that, we need to consider some additional features. Okay, so the key additional feature I'm going to be introducing is the energy required up to heat the Earth's surface. Okay, this is known as the surface heat capacity. So the surface heat capacity is often shown as capital C with a small s, the energy required to raise the temperature of a unit of area of a planet's surface by 1 degree. You should be able to recognize it having a very similar definition to that of the specific heat capacities we're working in our thermal unit. Units related to this are joules per meter squared per Kelvin. So it's the amount of energy per meter squared per area per Kelvin. And the formula which you're going to need to recognize for this is the surface heat capacity equals Q, which is the amount of energy coming in, divided by area, divided by the change in temperature. Okay. So that's our specific heat, surface heat capacity. So now let's fit it into an equation where we're looking at the energy coming in and out of this system. So the maths which is going to fit into our model. So we reckon the change in temperature should be equal to the amount of incoming radiation intensity, so that's the radiation from the sun, minus the outgoing radiation intensity. Now we're subtracting there because we should see that there's a difference, so there's some residual energy, but we need to times that by time to give us a total amount of energy, and then divide that by the surface heat capacity, and that should, in theory, and is shown in the data booklet, equal the total amount of temperature change. So intensity in minus intensity out times period of time divided by the surface heat capacity. Now we can use that formula to start to improve our climate model. Let's go through some steps here. So into practice, we're going to add this to the simple energy balance climate model which we've used before. We're going to assume radiation falls on the Earth at a rate of 364 joules per second per meter squared. You notice this is a slightly different value to one which we've used before. It's actually more accurate because it considers planet Earth as a sphere and recognises that only half of planet Earth will be absorbing solar radiation at a time. So this is the amount of energy falling per meter squared. Now the relationship between outgoing radiation and temperature, as we know from Stefan Boltzmann's law, is radiation out equals Stefan Boltzmann's constant times T to the power 4. So if we recognize that the temperature of planet Earth is 283 degrees Kelvin, approximately, we can work out that the radiation out is 364 joules per second per meter squared. Now, as we can see, any temperature change requires there to be a difference between the energy in and energy out. At the moment, we've got energy in and energy out being exactly the same values, so that means the change in temperature 1 year in this situation is going to be nothing. So the surface heat capacity is the amount of energy required to heat up planet Earth. As it happens, the surface heat capacity is 4.0 times 10 to the 8 joules per Kelvin per meter squared. Okay, so it does have a specific number. So as we said before, if the same amount of energy going in is coming out again, then there's going to be no change in temperature whatsoever. Now, if we, let's say, increase the solar radiation by 5%, we can go through this process and see what happens. So what happens here is we know that our key previous information is that previous radiation was 364, the initial temperature is 283, we know Stefan Boltzmann constant, and we know that radiation out equals Stefan Boltzmann's constant times T to the power 4. So now I've switched things. The radiation in is going to be slightly bigger. It's 382.2 joules per second. So what we have here is 382 minus 364. That means there's now a residual amount of energy which has been left. Multiplied by 1 year and divided by the specific surface heat capacity means there's an increase in temperature over 1 year of 1.43 kelvins. So therefore the new temperature after 1 year is 284.4 kelvins. So now our model is slightly more informed. We're not talking about a steady state, we're accepting that there can be some change. The interesting thing is, if I carry on through this process, what happens is that each year, if I accept that the temperature of the Sun has just increased by 5% and leave that as a fixed value, we recognize that after 1 year, the average temperature increases by 1.43 kelvins. However, what happens the following year, there will be a temperature rise, but it's going to be a smaller amount. And the following year, it's going to be a smaller amount. And the reason for this is because the planet will eventually find a new equilibrium. So there'll be a new balanced overall temperature, which is an interesting feature of models. So that's the start of thinking about models and how to extend what we've used before.